Welcome to Chapter 19. This is a very short introduction to network and distributed systems. So, in this chapter, we will discuss the advantages of having a distributed system over a single monolithic system, the network structure, the communication structure of a distributed system. After we have discussed the infrastructural aspects, we will go into network and distributed operating systems, the design issues with distributed systems, and clearly the most important facet or aspect of distributed systems, which is distributed file systems. So what are our objectives here? Our objectives are to explain the advantages of networked and distributed systems, provide a high-level overview of the networks that interconnect the distributed systems, discuss the roles, and also the primary issues that concern the design of distributed systems, and particularly how distributed file systems are different from regular file systems. So there has to be a difference. So we will primarily focus on the differences. So one disclaimer is due that this chapter is to a large extent self-contained. However, for a deeper understanding of networks and distributed systems, there are separate courses and separate books. Readers are referred to them. This chapter will only provide you a very brief, high level, and in most parts, a sketchy understanding of both of these important topics. So the key idea of a distributed system is it is a system of loosely coupled nodes which are interconnected by a communications network. So let's understand. What is a node? A node is basically an independent computing entity, which could be a processor, call it with a different name if you will, a computer, a machine, or a host. So a site will be the location of a machine, and a node refers to a specific system. So the key point over here is that, of course, a loose collection of nodes where so loosely coupled basically means that they don't share memory. So any loosely coupled collection of nodes is a distributed system, all right. But typically what we mean by a distributed system is that they appear to be one to an outsider. In a sense, internally they may be a loosely coupled set of nodes with their own network connections between them. But to an outsider, typically they will appear to be one. In a sense that, let's say, if you are accessing Amazon today, it appears as if Amazon is a single server. But that's not the case. Internally, Amazon has tens and tens of servers. And so a lot of servers, they do different things within Amazon. One server takes care of a shopping cart, one fetches the search results, one renders the screen. But we don't get to see all of that. So we perceive it to be one. So most of the time, when we refer to a distributed system, it conveys some kind of an illusion of oneness of being a single system to an outsider. So we are aware of many of these server client kind of systems, which are also distributed systems where we have a single server and we have multiple clients that are connected to the servers. And this would be like a star kind of network where you have a single server and many different clients. So this is also a distributed system which appears to be one. So nodes may exist in many different configurations. So what we have seen in the previous slide, we have seen a client server configuration where we have a single server and we have many clients. So the server and clients, they clearly have different responsibilities. In the sense, the server is in some sense special. So we have also looked at peer-to-peer systems where we have simple nodes which are just connected. There is nothing special between them as such. And each node shares equal responsibilities. And of course, somewhere in between, where we have a class of nodes that are slightly more privileged, that would make a hybrid configuration. And because they're all loosely coupled, they don't share memory, they communicate by passing messages. So all higher level functions of a standalone system can be expanded as such to also include a distributed system, in the sense that a distributed system is definitely a superset of standalone systems. But standalone systems, so it's superset in terms of infrastructure, but it is a subset in terms of features. In the sense, a standalone system can provide you many things which are fairly hard to guarantee in a distributed system. But if you can provide it, for example, if you can provide a distributed file system, it will have a much, much higher throughput. So now, what is the reason or what are the reasons for choosing distributed systems? So one is, of course, resource sharing. So where we share files or we share printers, or let's say for a database, for a distributed database, where one node is not enough. The amount of storage that is there in a single node is clearly not enough. So that's the reason we need many, many nodes to share the data. And also it is furthermore, it is possible that you can have some specialized processing units such as GPUs, which are quite expensive. So they need not be there with individual users, but they may be there in a distributed system which can be used. So what we have seen a data center in the previous chapter, what we have seen is that a data center offers many of these resources to users. And of course, if you have virtualization, then you have an additional layer of flexibility. So data center is also a distributed system. So a distributed system can be used in many different ways. So for example, we can use it in this fashion where we are sharing, where all the nodes are communicating to to implement a larger service such as a distributed database, for example, or we can use it as just one large computer where we just have a lot of virtual machines that are using their hardware. Another thing that can be done, which is also done in traditional supercomputers, is that we take a large computation, let's say a weather simulation problem. We create thousands of different small sub-computations where each sub-computation is dispatched to a separate node. And then, of course, the nodes communicate across each other, and then the problem is solved. So, of course, there are many additional challenges over here which are not there in a single machine, such as detecting and recovering from node failure, from site failure. Then, if let's say one computation is stopped in the middle, we need to either restart it somewhere else, or if we can recover some of the state, we can transfer the function and run it somewhere else. And then dynamically, we need to deal with these failures and reintegrate failed nodes once they come up. So pretty much reliability is the biggest challenge in distributed systems. If we would have had a reliable distributed system, reliable means reliable compute and reliable communication, most of our problems would be solved, but that is sadly a luxury that we do not have. So what is a network structure? So typically distributed systems are connected using a local area network or a LAN, which is designed to cover a very small geographical area. So we can have multiple computers, peripherals, as you can see. And of course, we all know what a wireless router is. So that also allows us to create a distributed system. So there are different Ethernet standards that are defined on wireless technologies. So that is IEEE 802.3, whose speeds are typically from 10 Mbps to 10 Gbps. And also there is a Wi-Fi standard which is 802.11, which speeds from 11 Mbps to 400 Mbps. So both of these standards are evolving, right? So Ethernet is typically used. So I stand corrected if I did mention that Ethernet is on Wi-Fi. So that's not correct. So Ethernet is typically a wired standard. So that's the way it had originally come up. So kindly, correct that. So it is defined by this IEEE standard, and this is a standard for wired connections as of today. And as you can see, Ethernet can be very, very fast. So even 10 Gbps or even higher speeds are possible. So Wi-Fi or wireless communication, on the other hand, is at a much lower speed range from 11 to 400 Mbps, and even getting 400, I can tell you, is hard. So local area network, as you can see, is contains a bunch of machines and peripherals, and then it can also contain Wi-Fi access points such that other computers and mobile phones, etc., can communicate with the Wi-Fi access point. And then, of course, the local area network is connected over here to the internet, to the rest of the internet, via what is called a wide area network or a WAN. So now coming to the wide area network, so this essentially links geographically separated sites. And when I'm saying geographically separated, there can be large distances between these sites. WAN networks are point-to-point connections. So in the older days, they used to be telephone lines, but now they are dedicated data lines, optical cables, microwave links. So there are all kinds of technologies out there, including satellite links. So these are all for having point-to-point links, and of course these are between routers. And the job of a router is to direct traffic from one network to another. So this basically allows all kinds of hosts on a wide area network, regardless of the technology, to talk to each other to communicate. So of course, as we have seen, so we will have these small networks of basic user devices. They will be connected with a LAN. Then there is one router over here. You can also call it a gateway. So of course, they do different things, but I'm trying to keep it simple over here. So the gateway server, whose job is typically often to route basically means given the IP address, send it to the right destination. So that connects with other backend links. So the providers of these links are typically called backbone providers, and they provide much larger bandwidth. So these bandwidths are typically of the order of 40 to 100 gigabits per second. And but the local internet providers or the local ISPs may be much slower, but the backend, the backhaul links are typically much faster, and they are also constantly getting upgraded. So the WAN and the LAN, they of course interconnect, and the interconnecting server is typically known as the gateway. And this is quite similar to cell phones. So even in cell phones, we connect to cell towers, and the cell towers connect to other towers and hubs and so on. So nowadays, in any case, phone traffic and data traffic is quickly becoming the same. But the basic idea, the key technology, remains the same. So in the wide area network, as you can see, we have many of these user processes which run on a host operating system. Then, of course, they connect to a local router, and their routers are connected to each other. And then we have these network hosts. And these network hosts kind of work like a hub where they may be connecting to other smaller subnetworks, or they may be a gateway to the WAN. So how do we name computers? So every computer in the network, in any network, is given a unique name. And every process in a system is also given a unique name. So the unique name in this case is just the process ID, something that we see in with the ps command in Linux. So we identify processes on remote systems with basically with a tuple, with a pair. The pair is the host name and the process ID. So typically in the internet, we need many kinds of standards because we have all kinds of hosts and all kinds of processes and so on. So we have the domain name system. It specifies the naming structure of the hosts, as well as it does a name to address resolution. So what happens is that in the internet, every machine has what is called an IP address, which is unique. And the IP address has many fields. It could be something like 212.13.13.161. So what the first part essentially denotes, so this is a 32-bit IP address. So there are two kinds, IP v5 and v6. So v6 is of course much larger. But in this case, this will kind of indicate the country, this the region within the country, this the sub-region, and then this the machine within the sub-region. But it is very hard to remember something like this. So we typically just type www.google.com. So in this case, Google is the name. So we require a service to resolve or convert the name to the address. And this process is known as DNS, or a domain name system. So if you were to look at a simple piece of Java code to look up the to do a DNS query, So what we do is we use Java's built-in inet address class, and then we read in the first argument. So the first argument is essentially the name of the website. And then this gives us the host address. So the inet address internally contacts what is called a DNS server. A DNS server maintains this mapping. If it does not have the mapping, then it can contact other DNS servers and so on. It can be a hierarchical process. Finally, it can fetch this mapping and then it can provide it to the process. So this is done whenever we type something on our browser, this mapping is done. So as we have seen in any kind of a network, we have many different kinds of technologies, and the technologies typically have a legacy of their own. They have a history of their own. So some technologies are new, some are old, some cannot be replaced. So that is why we need standards. So any network will have multiple layers, where one layer can run on one technology, another layer can run on another technology. We have a standard by which they communicate. So as long as the interface of the standard is fixed, the technologies per se or by themselves can change. So the lowest layer, or the layer 1, is known as the physical layer. It handles the electrical and mechanical aspects of the communication, I mean notably electrical, where you specify the voltages that are required to send a logical 0, logical 1, and so on. So it's mainly at the electrical level where you deal with noise and so on. The layer on top of it, known as the data link layer, it's also called the MAC layer, the medium access control layer. So it handles the frames or fixed length parts of the packets. Its main job is to basically, at least in a wired network, is to do error detection and recovery, figure out where there are errors in the packet. So there will be some errors, mainly because of network noise and so on. So some zeros will become 1 and some ones will become a 0. So in that case, our job is to detect the changes and then perform error recovery. Once that is done, so once between the data link layer and the network layer, once this is done, we are at least sure that the packets are correct. So mind you, in the network layer, we can happily change the network layer technology with some other technology. The rest of the layers will remain the same. They don't care. Or we can keep the data link layer and the network layer exactly the same. We can just change the physical layer. From a wired network, we can make it a wireless network. It will remain the same. And similarly, we can keep the physical layer and network layer the same and just replace the data link layer. It should work, at least in theory, absolutely fine. So the network's layer's job is that given the IP address, which as we have seen is a unique hierarchical address, its job is to compute an optimal route, let's say from the source to the destination via multiple routers, and figure out based on the IP address how to send a packet from point A to point B, and also ensure that proper information is contained such that we are not moving around in circles. So then, of course, we have a few more layers. So what I'm presenting over here is known as the OSI model, or a layered network model. So a few more layers are like this. We have the transport layer. So the transport layer sits on top of layer 3. So layer 3 is where we have the IP. It's also known as the IP layer. If you are using IP as the technology for layer 3, that is. So transport layer, the most important protocols in this case are TCP and UDP. So in this case, the transport layer is basically responsible for transferring full messages between clients. It's not at the packet level, it's at the level of full messages between clients. So its job is to basically take a large message, break it down into smaller packets, ensure that the packets are delivered, or let's say received at the destination in the correct order, and to also do flow control. So flow control basically means that it is possible that when the sender is sending a large message to a receiver, it is going via multiple routes. One of these could be really slow, and then this will become the bottleneck. So if we send a lot of packets, they will start queuing up, and then some packets may need to be dropped. That is why there is a need for the sender to adjust the rate based on how many packets are being done. And these algorithms to adjust the rates, this is known as flow control, typically a part of TCP, which provides reliable delivery, as opposed to UDP, which does not provide a guarantee of reliable delivery, but UDP is much faster. But because TCP requires reliable delivery and it has built-in flow control and retransmission mechanisms, it is typically slower yet reliable. And so this is the job of the transport layer, which is to ensure that messages, lock, stock, and barrel get from here to there. And let's say if there are errors, so errors are not the main issue. It's basically packet drops, but packets, of course, could be dropped because of errors or because simply there is too much of congestion in the network. So in that case, flow control is done. And finally, it is also possible that different packets in a message can take different routes. So reassembly in the correct order is also done. So TCP in that sense is a quite a heavyweight layer, layer 4. It's a fat layer. Layer 5, which is a session layer, this essentially implements sessions. So what you would have seen is that, let's say if you log in via SSH, or let's say you log into a website. So what happens is that I have my browser process, I have a server process. So let me call it the browser process and the server process. So what will happen is that after my password is entered and a mutual authentication has been done, a lot of messages can be sent between the browser and the server, two ways. And no additional authentication has to be done because they know each other. So this basic handshaking and the maintenance of what is a single session, this is done by a session layer. So this is a narrower layer, much narrower as compared to layer 4. And then there is a presentation layer. So once we have a session, we can exchange data. But of course, data may be in different formats in the sense that they could have different character encodings. Some may use ASCII, some may use UTF-8, 16, 32, and so on, which are Unicode formats. So there is a need for changing the character formats. And finally, the application layer, this comprises application specific protocols which deal directly with the user. For example, FTP is a file transfer protocol. Then we have remote login protocols, remote desktop protocols like RDP, email protocols, something that we have all heard, IMAP, POP, and so on. These are all email protocols, right? So we would have all heard of these things. So they allow users to build sophisticated network applications. So all of these protocol level things for directly building applications, once sessions and the session issues and presentation issues have been taken care of, is the application layer. So broadly speaking, we have these 7 layers in any network. So this is known as a network stack in any network communication protocol. The session and presentation layers have traditionally been de-emphasized. They are not all that important. That's the reason many times you will see people casually referring to it as a 5-layer stack. But actually it has 7 layers and all 7 layers are quite important. With the layer 4 being arguably the most complex, and layer 2 is also quite complex, particularly when you bring in wireless. The reason being that you will have to take a look into the channel quality, multiple transmissions in the same frequency, and packet drops, and so on. So layer 2 also, particularly with 5G and so on, has become quite sophisticated. So the OSI network model that I showed is basically a logical connection between two computers. And the 3 lowest layers are typically implemented in hardware, but it could be the 4 lowest layers also. It depends on the network card. And but as of today, in software, primarily TCP is still a software artifact to a large extent, even though not all the time. And but the network layer, link layer, and physical layer are almost always implemented in hardware, and they directly interact with the network and send data. But of course, the rest of the layers have their role to play in a software environment. So the protocol stack can again be seen like this, that we have the physical layer over here that comprises physical connections. The data link layer over here, which is the second layer, which is for framing. I mean, creating blocks of bytes, ensuring that there are no errors and so on. Then you have the network layer, which is for addressing. The transport layer, which is basically to divide a big message into packets and ensuring that the packets are reliably delivered. So flow control also comes as a part of that reliable delivery. And then we come at parts which are independent of the network. So the top three layers are independent of the network. So the session layer helps us create and manage and maintain a session. And then on top of that, we have a presentation layer for different character encoding formats and so on. And finally, we have the application layer, which is for application level protocols. So some examples are file transfer, document interchange, and email, and so on. So what typically happens is that if you look at any network message, you'll have a data link layer header and a trailer. So the moment it is processed by the data link layer, this part is removed and is provided to the layer on top of it. Again, there'll be a network layer header that is again removed when it goes to the transport layer. The transport layer takes it out. So on and so forth until the application layer takes out its header. So takes it out means it takes it out, it processes it, and what pretty much is left is the message. So the OSI model pretty much embodies or formalizes or finalizes much of the work that people have been doing since the late 1970s, and I would also say the early 1970s in this area. And finally, it became a globally adopted protocol stack in the sense that these standards have actually let the internet grow because we all have our own separate networks, separate hardware, and so on. But the internet technologies and the OSI model particularly allows them to talk to each other. This is the TCP/IP model, which has been adopted by virtually all the sites as of today. So, of course, the TCP/IP protocol stack, which will primarily terminate at TCP, has a fewer layers because it will combine functions of different layers. But still, the OSI model is still there. So I'll just show the relationship over here. So primarily when we talk about the TCP IP protocol stack, this is because TCP and IP are the most popular protocols. We tend to reason about network protocols purely in terms of TCP IP and things defined on top of them. So that is why people often refer to a reduced set of layers. So in many protocol stacks, they don't define or explicitly talk about the data link or physical layers or the presentation and session layers, but they primarily look at IP and they primarily look at TCP and its sister protocol UDP, but UDP does not provide reliable delivery. And of course, protocols at the application level, the most popular being HTTP, which is the protocol to retrieve and access web pages. But of course, DNS is also in there. We have discussed DNS. SMTP, which is for sending mail, FTP, which is for retrieving files, and so on. So, regardless of how we look at it, pretty much any practical implementation has to follow the OSI 7-layer protocol model. And but I mean, as for the sake of discussion, most of the time we only refer to these three layers: IP, TCP, and the application layer. So these three layers comprise what is called the TCP/IP protocol stack. So let's give a better example of a TCP/IP communication. So what we have seen is that every node has an IP address which is both segmented and hierarchical. So then if let's say we want to send a message from the sending node S to the receiving node R, then for the receiver's IP address, it will check what are known as routing tables, which essentially indicate that for some part of the address where to send the message next. Then after sending it there, the router on the way again uses the final host ID to determine where to send it next. So gradually more and more and more bits of the destination address match, which means it keeps on getting closer. in a sense that, let's say, I can send it to a router in that country, then to the region, then to the sub-region, and so on. So as we get closer and closer, we are also getting closer to the destination. So destination system receives the packet, but the packet itself may be part of a much larger message which has been split by TCP. So it waits till all of the sub packets come and then it reassembles them into a larger packet, into a larger message. So within a network, how does a packet move from a sender to a receiver? Well, so what happens is this is where the rest of the layers come into play. So what we have not shown in the TCP IP model, but they are there in the OSI model. So we can use one of the layer 2 protocols, for example, Ethernet or Wi-Fi. So the layer 2 protocols are known as MAC protocols, media access control protocols. So what they do, what we have discussed a few slides back, is that they provide a critical service of framing and error control. Of course, they do that, but they also do something else which is also quite important. So similar to an IP address on a LAN, so let's say I have one device over here and I have another device over here and I need to communicate. So then in layer 2, IP addresses are not used because IP addresses are artifacts of layer 3. So instead what we have is a MAC address which is not hierarchical or segmented, but MAC addresses could be quite random. So every device will have a MAC address, every network card will have a MAC address. See, if let's say we want to send a message from here to there, so what it needs to do is it needs to find out the IP to MAC address mapping protocol, the IP to MAC address mapping. So it uses the address resolution protocol or ARP to map the IP address and the MAC address. So once it has found the MAC address, it can directly send a message to that MAC address. So of course we can use broadcast messages over here, and the broadcast message is nothing but it's a special network address, so typically starts with 255, to signal that all the hosts should receive and process a packet. If if let's say in a LAN you want to broadcast it to everybody, often that is not required, but sometimes it may be required, particularly if you want to send an emergency message like a shutdown message. And broadcast messages always remain within a LAN and they are not forwarded by the routers or gateways to other LANs. So the key point over here is that you need to understand that an IP address is primarily a layer 3 concept. But let's say that I am over here, so I am a router over here. So what we typically do is that if I have an IP address, IP address is not useful the moment I come inside a LAN because I've already reached the correct LAN. So let's say this was the router in the LAN. This is the final destination, right? So I should not be using the R symbol here. Let's call it the router in the LAN and let this be the final destination. So in this case, the router does know the IP address of the destination, but that's not going to cut any ice over here because what we need to know within the LAN is the MAC address of the destination. The only way that this can be done is if we can somehow map the IP address to the MAC address, and that is why we have a separate protocol, which again has its IP to MAC address tables and so on. It's known as the ARP protocol. Once we find the MAC address, so then a layer 2 protocol will allow effective delivery of the packet from the router to the destination using the MAC address. So that's the key idea over here. This is the structure of an Ethernet packet. So what we see is that the first 7 bytes are the preamble. So the preamble is a fixed byte pattern to indicate that this is the start of a packet. Then we have a frame delimiter to say that we are starting the frame. So what follows are the destination and the source address. So basically we either have 2 or 6 bytes over here. So these are the MAC addresses or the L2 addresses that we are talking about. So they are not IP addresses, but they are dedicated addresses in the Ethernet protocol to identify the nodes. basically the network cards that are a part of the LAN. Then we specify the length of the data section, which means how much of data we are carrying, which is the actual payload. The data is over here, it is optionally padded. And so the reason that padding is done is to basically ensure that the size of the packet is at least 64 bytes. So that is the minimum size of the packet. So if let's say our payload is less than that, there is a need to add an optional pad, which is nothing but junk data, but that is required to ensure that there is at least a minimum Ethernet packet size. And then at the end, we have a checksum, which is nothing but the error detecting code to find out if there is an error in the data or not. So sorry, the error in the packet or not. So we have been discussing two kinds of transport protocols, UDP and TCP. So the key idea is that layer 3, which is the networking layer, operates on the basis of IP addresses. We send a message from one IP address to the other. So from a source IP address to the destination IP address. At the destination, we have dedicated processes that are waiting for the message. So waiting for the different packets that are a part of the message such that they can be reassembled in the correct order and then they can be presented to software. So this is the job of layer 4, the transport protocols, out of which TCP and UDP are the most popular. So they identify themselves in the sense that a single IP address can have multiple TCP or UDP connections which are identified with a port number. So typically it is an IP address colon port number, that's the format. So this allows a single machine with a single IP address to have multiple client server connections with multiple machines. So of course they would be communicating with different ports. And for many protocols, the port is standardized. So for FTP, it is port 21. For SSH, it's port 22. SMTP port 25, HTTP port 80, and so on. So HTTP is the web protocol. So for that, we use port 80. For email sending, it's port 25, and so on. So the transport protocol can be simple like UDP, or as we have seen in the case of TCP, it can be far more elaborate. So UDP is typically is used in a scenario where we do not want any guarantee of delivery, in the sense that we just send packets and we are not really concerned if they are received in the order in which they are sent, or they are not received in order. And furthermore, there is no need to maintain a connection between the sending machine and the receiving machine. So no connection is set up at the beginning of the transition to set up any kind of state at both sides. So pretty much you send packets and then you tear it down. So UDP packets are known as datagrams. So you can think of it, telegram is to mail, datagram is to datum on the internet. So in the case of UDP, what can happen is that the client sends an initial request for data to the server. The server will start sending data back to the client. So in this case, it will actually send a bunch of packets. So it is possible that one of the packets may get dropped. That's fine. So basically, the client will somehow have to recover or somehow have to take care of the dropped packet, but the client will essentially recover. TCP, on the other hand, is designed to be reliable. It is designed to be connection oriented. So it is designed that connection oriented basically means that both the sender and the receiver, both of them maintain some state. And so they establish a connection, and the connection essentially creates that state such that they can synchronize and coordinate the process of data being sent from the sender to the receiver. So TCP does provides an abstraction as if the message is being seamlessly sent from the sender to the receiver, but that is of course not the case. So what can happen is that packets can get dropped in the middle. So or there could be a lot of congestion. So all of those things are transparently handled by TCP. So whenever the host machine sends a packet, the receiver needs to acknowledge it, right? This was not there in UDP, this is there in TCP, that every packet that is sent has to be acknowledged. And if an ACK is not received before a certain timer expires, it means the packet has most likely been dropped. So the sender will resend. So it is of course possible that two copies of a packet may arrive at the receiver. That's the reason every packet has a unique sequence number which is used to identify the packet to the receiver. This ensures that duplicates are not received, and furthermore, packets are received at the receiver in order. So the TCP header allows the sender to embed sequence numbers to put packets in order. And also this allows both identification of duplicates and removal of duplicates, as well as ensuring that a sequence is maintained. In a sense, the order in which packets are sent, they are processed in the same order. Of course, setting up a connection in TCP is more expensive. So there is a three-way handshaking process where a set of it's a three-way connection over here. It's known as SYN-ACK and SYN-ACK. So basically the key idea over here is that we send a set of control packets to set up the connection, and after that we just send regular data packets, and finally the connection is torn down. So whenever the in a so this shows a typical data transfer scenario with TCP where data is sent with sequence number 904 and acknowledgement comes for 904, and then again from the other side data is sent with sequence 126, right? So the server sends it, the receiver sends an ACK. But now assume that data with sequence number 127 gets deleted or gets dropped. So in this case, what happens is that an ACK is not received. So basically, the server retransmits the same packet and then it receives an acknowledgement for it, which means that in this case, the packet has not been dropped. Now consider the other scenario where we send a packet with sequence number 128, where the acknowledgement gets dropped. So when the acknowledgement gets dropped, of course, the server has no idea of knowing what exactly happened. So it sends one more packet with sequence number 128. In this case, it is correctly received, but mind you that two duplicates are received, both with the same sequence number. So that's the reason the one of the packets can be dropped. That's fine because now we have a copy. But at least the client in this case will be sure that the acknowledgement got dropped in the network. So it will send an acknowledgement again. So there are of course some optimizations over here. So the receiver can send a cumulative acknowledgement, acknowledge a series of packets. So this will reduce the traffic in the network. Furthermore, the server can also be slightly more speculative in the sense that instead of waiting for an acknowledgement which needs to come immediately, it can send multiple packets and wait for all of them to get acknowledged. So this will increase the network throughput because we are kind of relaxing our requirements a little bit. Of course, as we have been hinting for quite some time, there are two very critical aspects of TCP, which are flow control and congestion control. So flow control basically means that it prevents the sender from overrunning the capacity of the receiver, or let's say overrunning the capacity of the network. So consider a sender and a receiver and a message travels through the network. In this case, it is possible that there is a bottleneck somewhere, or maybe there is a slow link and packets get dropped. So in this case, what will happen is that the sender needs to detect this. So the way the sender will detect it is that it will basically see that acknowledgements are not coming for the packets that it is sending, which means that in a sense that they are getting dropped in the network. It will sense this and it will reduce its rate of sending. So of course, how it will reduce its rate of sending is a research area in its own right. So this is not something that we will discuss right now, but at least the idea should be clear that TCP does flow control and it also does congestion control, where it makes a model of the congestion in the network, and again combined with flow control modulates the packet sending rate. So now after we have discussed TCP and UDP, the idea is to build applications on top of TCP and UDP. So there are operating systems. So sometimes they are not full-fledged operating systems, but more like software layers that provide some kind of a distributed service. So they are known sometimes as network operating systems, where users are aware of the multiplicity of machines, which essentially means that users are aware that there are actually 20 different machines, and some operating system is running where it is making it easy to run programs on these machines. The other is we could have a distributed operating system. So some refer to some avatars of it as middleware as well, where the users are not aware that there are actually multiple machines. So the users feel that all of these machines are actually the same machine and it is appearing to us as one. So whenever I send a command, it is as if a single machine is working on our command. It is appearing as one. And that's the key idea, that it is not one, but is appearing to be a single machine. So needless to say, a distributed operating system is easier to program. So coming to network operating systems where users are aware of the multiplicity of machines. So the key idea is that we need to achieve multiple things in such a scenario. So a classic example of a network operating system, where of course the word operating system may not be used, it may not be the most appropriate, but it would be basically that I have a client machine here, like my laptop here, and I have a remote server. I log into the remote server using SSH. In fact, there may be multiple remote servers. I can specify the host name or the IP address, and then I can log into them. So this is of course an example of using the resources of another machine over the network. Then I can transfer files and I can do many more things. So for example, I can access Microsoft Sky Drive or Google Drive. So in that case, what I'm doing is that I am using them as file servers for me. So these are all examples, these are all avatars of network operating systems. So of course, nowadays with the cloud and so on, many of these definitions per se have blurred. But the key idea is that if let's say I have a bunch of machines and somehow I can access them, I can run programs on them, I can store files and data on them, and I can control them, I have an instantiation of a network operating system broadly. But what is much more interesting is actually a distributed operating system that we see next. In a distributed operating system, as we have seen, users are not aware that actually there are multiple machines, which means that we need to support two features: data migration and computation migration. So in data migration, what happens is that across machines, we transfer either files or portions of files to ensure that I perceive a single file system. Even though I may have hundreds of machines, I actually perceive a single file system. The way that this will work is that if I log on to any machine of that is a part of a distributed operating system scenario, then I can access all my data regardless of wherever it actually is. So if you think about it, Google has so many servers that store our data. But the moment I log on to Google's site, I don't actually perceive the fact that there are so many machines. I actually find that wherever I log in, I'm able to see my data, access my photos, and so on. The other thing is that if I'm running a program, so assume that I have a large number of machines and I'm running a program. One of those machines goes down. So what we have seen in the previous chapter is that the computation can migrate, and this is invisible to the program. So this has to be supported. So this is one aspect of computation migration. There are a few more aspects. For example, it is very well possible that I may be running uh, a program over here, and then maybe some other function is hosted over here. So I'll make a remote procedure call and then I will access that function. Or I can use a messaging system and then I can get computation results or pass computational arguments. So that is one way where the computation can be transferred across the system, which basically means that either I can migrate the entire computation or I can keep some of the computation here and just migrate the functions, which can be easily done by the RPC mechanism, where instead of executing the function on this machine, I can execute it somewhere else. But as far as an outsider is concerned, the outsider still sees the entire system to be one and all the nodes within the system, coordinating the entire process of achieving a higher level task and migrating data and computation between them. So when you're talking of process migration, where want to execute some process or some parts of it at different sites, we have to look at many things. We have to keep many issues in mind. One is load balancing, which means that the load on any machine should not be disproportionately skewed. So if I have, let's say, 100 machines, roughly the load on all 100 of those machines should be equal. The second is that I can or I should aim to speed up my computation as much as possible, which means that if I have a large program, I can break it down into small subprograms and I can dispatch these programs into different machines where computational speed up may not be possible all the time, definitely possible sometimes. And also, I can specify a software and hardware preference. So, what we have seen in the previous chapter on virtual machines, that if let's say I have special hardware like GPUs or so on, I can specify that my computation should run on that node with a GPU, for instance. And if I have a special software preference, I can also specify that my computation needs to run on a certain node that has a certain software installed. For data access, I can either bring the data close to the process or take the process close to the data. So typically both the paradigms are popular. So what happens is that if I have a process running over here and let's say some data resides over here, then maybe some portions of it which the process will use can be cached locally for faster access. Or the other is that I can migrate the computation to where the data resides, such that again the data is available locally and the access is much and the entire computation process is much faster. So some design issues of distributed systems. So as we have been arguing, the biggest issue with distributed systems is robustness, which basically means that how far can it withstand failures. The second is transparency. In terms of the fact that nodes will get down, that's the reason both data and computations need to move and migrate. How easy and transparent it is, and particularly a user from outside should not be able to see it. Scalability. So, what typically happens is that let's say I have a data center, and so consider a data center for Amazon. So, in a normal day, it will not see that much of load. But let's say at the time of a festival like Christmas, for instance, or the New Year's Eve, where people will actually buy a lot and gift a lot, what happens is that there is a huge amount of activity and there is thus a need to add more machines. Can this be done seamlessly? So the entire field of distributed systems pretty much has been looking at this for quite some time now, ever since cloud computing became popular. So the key idea is that if let's say I need more machines, can I just bring in more machines and put them into my system and expand my system and then take them away when the load reduces? So robustness is again can be a software failure, can be a hardware failure, can be a network failure. It doesn't matter whatever is the degree of the failure, but we have to define what is the amount of fault tolerance. And naturally, more is the fault tolerance, the better. But of course, that does place limits on performance, and that also places limits on the correctness of our program in the sense that if we want a lot of fault tolerance, then we will not be able to afford certain programming paradigms and vice versa. Failure detection is hard in a distributed system, but again, the key idea is that we have a heartbeat protocol. So if there are two sites A and B, so what they will basically do, which is similar to TCP in a conceptual sense, they will periodically send messages to each other known as heartbeats to essentially tell them that they are alive. If A does not receive heartbeats for B for a certain time, it will assume that it has gone down. It is of course possible that a message may be lost in the network, but let's say after several such rounds, A will figure out that B has gone down. So of course A can further prompt B by sending an RU up message to B, and still if it doesn't receive a reply, it will know that B has gone down for sure. And the RU up message can have a higher priority in the network. So now the idea is that if B goes down, what happens? Well, a lot of things can happen. So basically, either A knows the reason for the failure. In some cases, it may, particularly if it has access to a third party who knows more about B. Otherwise, the protocol needs to adapt to this scenario and ensure that the overall computation goes on seamlessly even when B is down. So this would essentially require reconfiguration and recovery, where let's say that depending upon the type of the failure, something needs to be done. So the first is that the rest of the nodes have to be informed that node B has failed in this case. So in this case, if A is aware that B has failed, it can just send a broadcast message to everybody else saying that, look, B has failed. The other is that other nodes, including A, have to continuously be pinging B to find out if it has come up. So if it comes up, then again we need to send a message that, look, B is back up. But till it is not back in action, the system has to reconfigure to exclude B and still keep running. Now let's come to transparency. So we have been looking at or discussing location transparency. So the key idea is that consider a bunch of machines and we want all of them to see the same file system. So in many academic environments, particularly with Linux machines, we have the NFS file system, the network file system. So in that, what happens is that there may be a lot of machines, but they perceive that the file system is the same. So all of them see the same view of the file system. So this is also similar to, let's say, OneDrive or Google Drive, where wherever we access Google from, we perceive the same file system. And let's say you make a change. If you and I share a directory, I'll be able to see it immediately. So the NFS file system is definitely one example of location transparency. The other is that kind of allowing user mobility. So which is allowing the user to just move around and log in on any machine in the lab. So what happens in many undergraduate labs where there are particularly a lot of students is that if there are a lot of lab machines, a student may want to work today on machine A and tomorrow on machine B. Both the machines have to recognize her credentials. That is why we have the Ldap protocol, which essentially provides a common login system for a bunch of disconnected machines over the network. And finally, scalability. So you come back to my Christmas and New Year's example. So I said that whenever the demand increases, the system has to react gracefully and increase the load. For that, it should be able to accommodate more machines and add more resources such that they can take the load. And furthermore, if let's say we are using storage and network resources, so we can, instead of adding more storage, we can increase the amount of usable storage by basically compressing data, particularly if there is some amount of redundancy, and deduplicating data. In a sense, assume that two users are exactly writing the same file. Or consider a case where I'm sending an email, I'm sending the same attachment to 100 people. There is no need to store 100 copies of the attachments. We can just store one attachment and just have pointers in the mail, internally, that is. So, all of these things are done to ensure that a distributed system remains scalable. So, now we'll come to distributed file systems, which is a glowing example of distributed systems where a bunch of clients and storage modules see a single file system. Even though the files are physically dispersed among the storage devices, we don't actually get to see that, at least from a functionality perspective. So a distributed file system works like this, that we have a service. So a service is basically a software entity that runs on one or more machines, and it provides a service for processes on that machine. So we can have a server which is the original host of the file system, in the sense that the server is the default home of all the files. And then we'll have a large number of clients that will connect to the server and basically use the file system. So to ensure that NFS looks like a regular file system, it has been made more or less compatible with the Unix file system, where we can create a file, delete a file, read, write, and so on. So the client interface as such is transparent, in the sense we have discussed the issue of mount points and so on long back. Here the idea is that even if a file system is mounted on NFS, the moment it comes to a local file system, we assign a mount point to it, and the user can happily traverse the entire file system. So basically go through the directories, and the file system layers do all the hard work, do all the plumbing. So in a sense, the entire operation of navigating the file system looks very straightforward to me. The reason being that internally everything is being taken care of, and all the machine to machine communication and so on is hidden from me. So there are two widely used architectural models in this. So one is a client server model, something that NFS uses, where we have a server which is a default home and then we have clients. The other is a cluster based model, which we'll discuss. So the challenges that include is that how do we name the file systems, provide location transparency, and so on. How do we access files that are held remotely? And the other idea is that we may want to cache files or portions of files, because if there is, let's say, a remote machine and then there is a local machine and the process is running over here, if there is a file for reading every byte, we don't want to make a network call to the remote machine. What we would instead like to do is we would like to cache a part of the file locally and keep reading it from there. But the problem that can arise is that if, let's say, there are two local machines that are working on the same file, they can make conflicting modifications to the same file block, and then the issue of consistency and correctness will come up. So this needs to be handled. So our current lecture ends over here. So the next lecture we will look at different kinds of distributed file systems. So DFS here stands for distributed file system. So we'll look at regular NFS kind of file systems, and we'll also look at cluster based file systems. So that will be the second part of the lecture for chapter 19. So the first part ends over here.